All right. Hi, everyone. I'm Jose, and I'm going to be presenting Augury, using data memory-dependent prefetchers to leak data at rest. This work is done in collaboration with Michael Flanders, my co-first author, as well as a broad team across the University of Washington, Tel Aviv University, and the University of Illinois at Urbana-Champaign. There is a vast body of work on leveraging microarchitectural side channels to leak data. Attackers have used everything, from speculative execution and computation simplification to stream prefetching and even on-chip interconnects. However, all these attacks have something in common. They all leak architecturally accessed data. Consider a cache side channel attack, where the adversary is targeting this secret. First, the data is going to be read into the core, either speculatively or non-speculatively. And then it's going to be acted on by an instruction. This action is going to change resource usage in an operand-dependent fashion. In this case, that might be through the use of the secret as an offset into an array as inspector. This operation leaves behind a trace in the cache, which an adversary can then observe. In this paper, we present the first microarchitectural attack, which leaks data that was never directly read into the core, either speculatively or non-speculatively. That is, our attack now looks like this. The secret data never flows into the core. This attack is made possible by a previously unreported class of prefetcher, a data memory-dependent prefetcher, or DMP. Unlike well-known and widely implemented prefetchers, whose behavior is purely a function of the program address pattern, DMPs read and initiate cache fills based on the contents of program data memory directly. We leverage the DMP to leak memory without relying on transient instruction execution. Prefetchers are next-in-sequence address predictors that proactively fetch data into the cache to help hide memory latency. Importantly, they live in the memory system and are software transparent, meaning that they're unaware of any program semantics, including memory bounds. For example, let's consider this piece of code that I'm sure we've all written in the past. We're simply traversing an array A here at a constant stride of k. Now the prefetcher is going to see our memory accesses, recognize what they are, and begin issuing prefetches. Now we're going to see a very significant speed up on this code pattern. It's a very easy pattern to predict. Now essentially, we're going to make a small but very significant change. Let's add a pointer dereference of each element in the array A. Now, the classical prefetcher at this point is going to still prefetch A, but it's going to throw up its hands. There's really nothing it can do about the pointers. Except here is where DMPs come in. Now, DMPs prefetch irregular, data-dependent access patterns, such as pointer traces or indirections. These data-dependent access patterns require understanding dependencies between the address pattern and the contents of memory itself. Where the classical prefetcher was looking at the outgoing addresses, the DMP is monitoring both outgoing addresses and incoming data, and it's matching them. It's reading the data that's coming in, it's interpreting it, realizing that, hey, this is a pointer, and I'm going to dereference it. Now, of course, whatever the DMP does is going to leak something about memory. Let's look at it a different way. We're streaming through this array A, performing dereferences. A is prefetchable by a conventional prefetcher, but the conventional prefetcher doesn't know the bounds of A. It lives in memory, so it overshoots and accidentally brings the secret pointer into the cache. Now, if we're on any other system, this is actually no problem. The secret pointer is in the cache. We might not have even speculated past the end of the loop. We might be employing a spectrum mitigation like SLH. It has not been architecturally accessed, and the secret pointer is actually safe. But now we add in a DMP. The DMP also doesn't know the bounds of A and says, hey, you know what? I'm going to prefetch this for you. I'm going to dereference it. And now I've brought it into the cache, and now I've created a channel which an adversary can observe. They can realize, hey, this was a pointer, it got brought in. How then can we prove the existence of such a DMP in the M1? Well, DMPs try to detect associations between addresses outgoing from the core and data incoming to the core. So to test for the existence of a DMP, we need two programs which are the same except for this association. We give details in the paper, but I'll explain the high-level idea here. we're going to start with an access pattern that we hypothesize should be prefetchable via DMP. Next, we're going to construct a second program, a baseline. Now, this program is going to have the same outgoing addresses and execute the same instructions as the first, except we're going to get rid of the incoming data. The addresses that are dereferenced are going to be generated on the fly using a PRNG that has the same seed as what we use to populate array A. This is the average access time for that baseline, and this is the average access time for the pointer-based access pattern. There's a significant speed up. This is evidence that a DMP capable of prefetching through exactly this access pattern is present in the M1. Similarly, we tried other DMP-friendly access patterns and found that they do not derive speed up. Finally, we performed multiple tests and took measures to ensure that this behavior is the effect of a DMP and not another optimization, like, say, speculative execution. There's a lot of reverse engineering details that go into this. Unfortunately, I'm going to have to omit them for time, but they are in the paper, and I encourage you to take a look. So let's discuss how we can exploit this DMP. In the paper, we demonstrate a proof of concept which uses the DMP to read past the end of a buffer. So a conventional prefetcher overshoots the bounds of the array and allows the DMP to dereference a pointer in memory which would not have otherwise been dereferenced. This action allows an attacker to determine whether a pointer is valid and possibly even the value of the pointer. We also target address space layout randomization, or ASLR. ASLR is a widely deployed defense which prevents attackers from knowing a priori the locations of important parts of a program in memory. It does this by randomizing the locations of portions of a program, such as the stack, heap, code, and libraries. Breaking ASLR, that is discovering the virtual addresses of code and data pages, is a core step in many larger exploits. We show how the DMP can be used to check whether an arbitrary pointer maps to valid memory, and thus aid in breaking ASLR. Using the DMP, rather than, say, a cache side channel, removes the need for knowledge of the cache system or for creating eviction sets and is significantly less noisy. Next, let's take a look at a fascinating scenario, speculative load hardening. SLH is a defense against conditional branch-based speculative attacks, Spectre variant number 1. It's going to take this code pattern and add a branchless recheck of the conditional within each iteration. Now, in the first pattern, we have a loop which can easily exceed its bounds, and it's going to bring something into the cache. We're going to see our pointer get brought in, possibly dereferenced speculatively. SLH, what it does is it ensures that the load will behave normally only if the branch has been predicted correctly. From the point of view of the core, we're safe. Critically, that is only from the point of view of the core. That is not what's happening in memory. Let's see what the memory system sees for our SLH protected access pattern. Well, we're going to go through our array A, performing our dereferences, and it should look pretty familiar by this point because it's just going to overshoot and perform the dereference. This is a fascinating scenario because it turns out that if you have Spectre vulnerable code, you protect it with SLH, you run it on the M1, you're going to see the exact same behavior as if you hadn't used SLH at all. This is not a shortcoming of SLH. It's a fundamental limitation which applies to any core-centric defense against speculative attacks. Augury attacks are the first speculative attacks in the memory system. Before today, that wasn't actually an attack surface that defenders had to worry about. How then might we go about mitigating leakage over the DMP? A possible solution is similar to the one adopted by many Spectre defenses. Don't keep secret data in the same virtual address space as the adversary program. This is going to prevent your conventional prefetcher from overshooting and reaching the secret in the first place, and so the DMP is going to have nothing to translate. Where SLH protected against transient execution attacks in the core, this defense protects against transient execution attacks in the memory system. Now, Spectre vulnerabilities have already put all of a process's virtual memory space at risk of being leaked. So we're seeing wide-scale deployment of spectrum mitigations which remove the most obvious sandbox or user space to kernel attack surfaces. Let's take a step back, however, and consider this in the face of general DMPs. There is no guarantee that all DMPs will have a shorter reach than Spectre. The M1 DMP reaches a subset of the memory that is reachable by Spectre, but there is a very large design space for DMPs. There's no saying that there won't be a future DMP that can reach beyond what a Spectre attack can. Beyond this, in our experiments, we repeatedly unintentionally activated the M1 DMP, solely by storing pointers on the stack. It's an incredibly aggressive DMP, and it's possible for a program to be accidentally leaking data, even without any intervention by an adversary. We must also consider these cases where a privileged, non-malicious program contains latent DMP gadgets. These must be detected and removed. While exceptional now, we expect that this DMP is only the first of many DMPs to be deployed across all architectures and manufacturers, a trend further suggested by recent patents of different patterns. Consider a simple extension to this pointer tracing pattern, one which allows for nested pointers. Or consider an indirection-based access pattern, which can also be extended to handle multiple levels of indirections. Some of these have been patented. Despite being a variant with strictly limited leakage, we demonstrate that the M1's DMP is capable of being abused by an adversary. Beyond the implications for the M1, our work also provides guidance for the reverse engineering and security analysis of any DMP system. Relevant axes of interest are: what are the preconditions for a DMP to activate? What function of memory values is transmitted? That is, what can leak? In the M1's case, that's pointers. How can the adversary receive the transmitted values? And what memory is accessed to inform prefetching? Finally, the optimizations which exist in processors today only constitute the tip of the iceberg of what microarchitects have dreamt up. We learned about the M1's DMP during a study of these other exotic microarchitectural optimizations, each of which has novel leakage implications. Considering Moore's law, this is likely only the first of many new exotic optimizations we'll find in the wild. We hope that both these works can serve as a first step for more systematically studying such microarchitecture, so that security considerations can inform the development of secure and performant optimizations moving forward. Thank you very much. I'm happy to take your questions.
Okay.
Daniel Morimi from UCSD. My question is, what did Apple respond to this?
So we've disclosed it to Apple, and as far as we know, there's no way to just disable it. So it's in the iPhone, it's in the M1, from the M1 to the M1 Max, and it's just out there.
And they don't have any plan for mitigation? Or?
Not that we're aware of.
Thanks.
Yeah.
So a follow-up question on that one, and then a second one. Do they go into this ignorant or reckless?
That's an excellent question. To be honest, it's a very interesting access pattern. It's not incredibly common. But that said, I think what we're seeing here is the classic conundrum, performance versus security, right? This thing actually gives you great performance. If you're on an M1 and you're doing this pattern, you're seeing 8 to 12x speed up. That's incredible, considering how bad this is for the memory wall. So there's really no telling. I can see a very good argument for including it performance-wise, but it can be bad. It can be very bad from a security perspective.
Yeah. So sort of a follow-up detailed question. I'm curious what range you observed in the DMP on the M1. So maybe this is actually more of a question of like the range of the linear prefetcher.
I'm sorry. You mean the reach you can have in memory?
Yeah, exactly.
Yeah. So it depends on the conventional prefetcher, right? Your conventional prefetcher needs to be able to reach something. So past the end of your loop, you can reach up to 64 kilobytes.
I see. Cool. In pointer space, that's a lot.
Yes.
Yeah. Oh.
Yeah.
Okay. Thank you very much.
Yeah.
one of the main defenses against side-channel attacks in cryptography is constant time programming, which assumes that all leakage is address-based. How can we fix cryptography now?
Yeah, that's an excellent question, and an open question at that. So one of the important things about this prefetcher is that it's not IP indexed. So in fact, if you have completely separate instructions, completely separate memory accesses going out to memory that look like this pattern, the DMP is going to turn on. And so say you go in, you make your program constant time, you remove all loops, you can still have a gadget for the DMP.
So how can we avoid it?
I would call that future work.
Have you searched for similar patterns on other processors?
Yes, we've tested a wide range of processors, Intel and AMD, and we've had no luck either with this pattern or with the indirection-based pattern that you saw here. They are patented. They're, as far as we know, just not available in the wild just yet.
Any further questions? Okay, so we'll thank Jose again.